multi-step methods. And this is going to lead to our nonlinear, the case of our nonlinear problems. So some of the methods that we have presented for linear equations are really not well suited for nonlinear equations. I already said, for example, that leapfrog can become unstable if you put it in the Burgers equation. So multi-step methods are methods that use, these are finite difference schemes which use split time levels. And these in particular are especially well suited, they work very well in nonlinear hyperbolic problems. They're also called predictor-corrector methods. Because in the first step, you have a temporary value for the dependent variable, your solution, and this value is, say, predicted. In the second step, a corrected value is computed to provide the final value. So one of the most renowned of these is called the Richtmyer Lax-Wendroff, or the two-step Lax-Wendroff. There are two variants of this. The variant 1, which is due to Richtmyer, is at point I. So remember, we have two time levels, but this refers to the point in the mesh. And the second variant, which is the more widely known as the two-step Lax-Wendroff, is at the midpoint, I plus 1/2. So let's see the version 1. Let me call it version 1. And in both cases, both version 1 and version 2 will have always, for step 1, a Lax-Friedrichs method at time level n plus 1/2. So remember, the Lax-Friedrichs method introduced this trick of replacing ui by the average value of the mesh points on either side, and so we would write u n plus 1/2. We're going to this intermediate value at I, and this will be usually minus un plus 1/2 in this case at I, but instead we put the average value between ui plus 1 and ui minus 1, and I said that wrong, is actually the previous time set, so that should be n. And this is divided by, in this case, delta t half, because I'm only going from n to n plus 1/2. And this is equal, I'm using again my linear advection equation, so it's minus c, and we have here du dx, so we write our, let's write a central difference for u dx, so we have u n I plus 1 minus u n I minus 1 and 2 delta x. So So this is our Lax-Friedrichs method. Central difference in space is stabilized by the trick of replacing UIN by the average. Okay. Step 2 is a leapfrog. But note this is going to be, again, with delta t half. And remember the leapfrog is looking at, usually would be un plus 1 minus un minus 1 divided by 2 delta t. So we're looking at both sides of our delta, our time level. So we write it un plus 1 minus un I, and this is a leapfrog with delta t half. In the leapfrog you would have, well, let me write so that we understand what the leapfrog would be. Leapfrog would be, so let's remember, leapfrog was ui n plus 1, ui n minus 1, and this is divided by 2 delta t. So here we would have 2 delta t, but I already have delta t half, so the 2 goes away, is what I wanted to make sure you see. Okay? The 2 cancels out. Equal to minus c, and here I am going to go to, I'm going to use, so with this step, which is step 1, I get u at every mesh point, but time level n plus 1/2. And those are the ones I'm going to use here in our next step. So I will have here u n plus 1/2 at I plus 1 minus un plus 1/2 at I minus 1. So we've taken these and we're going to use them here. And this is divided by 2 delta x. Okay, so I'm using this formula, but the point in the middle is n plus 1/2. So that's the important part that we mean by this with delta t half. So this is what we're using here. And this guy is what is going to be the result of step 1, which I put in step 2 here. Okay? So this is the predictor step, gives me un plus 1/2. I put it in here and I get un plus 1. Okay. So I'm going to rearrange terms in the next slide. I'm just going to rearrange these guys a little bit to isolate, of course, this is what we want. But I'm going to rewrite this equation with this one on the left-hand side and this one on the left-hand side on their own, so you can see the 2 equations cleanly, the way that you would program them. This is our kind of transposed version of the equation that goes into your computer code. And so we rearrange to get our 2 steps. un plus 1/2 at I is equal to 1/2. This is the trick used in the Lax-Friedrichs, which is to put the average. U I plus 1 and ui minus 1. Of course, this is at time level n. Minus c delta t over 4 delta x, 4 carried over from our previous derivation, and we have u n I plus 1 minus u n I minus 1. So here's our first equation, and our second equation takes us from n plus 1/2 to n plus 1, and this is equal to uni minus c delta t divided by 2 delta x, and here we have the half points in time, u n plus 1/2 I plus 1 minus u n plus 1/2 I minus 1. So here are two equations. You see the first equation gives me all the values that appear here on the right hand side for the second equation. We need these two sub-steps within each time step to get our final solution. This method is stable for a courant number less than 2 and version 2 of this, the only difference is that we still have a first step in Lax-Friedrichs, but the only difference is that we're going to use point I plus 1/2. So step 1 again is a Lax-Friedrichs, but on I plus 1/2. So I can rewrite immediately from here. Change colors. U n plus 1/2 I plus 1/2 equal to the average of un I plus 1 and un I minus 1, and our other term, and here I'm going to have a 2 delta x because I have used delta x half here, and we have un I plus 1 minus un I. So this is, so the midpoint here, the midpoint between these two is, as you can see, I plus 1/2. That's the midpoint of these two. So that's why from here to here we have a difference in these two. This one was I minus 1, this one is just I, and it's just, we're taking a different point reference, a different midpoint here. So second step here, u n plus 1 I, we get now the final answer, equals u n I minus c delta t divided delta x, and here we use the predicted values at n plus 1/2 and also I plus 1/2, and this is going to be n plus 1/2 and I minus 1/2. So it's a center difference where I is my central point, but I'm looking at 1/2 delta x on both sides. So this one is stable for c delta t over delta x less than 1. So now let's look at the, to understand this a little bit better, let's look at the stencil for this. So the stencil would look, I'm going to use red, no, let me use this one. Okay, I'll use the blue. So we have one, that's going to be n plus, this is going to be n plus 1. This is going to be n plus 1/2, and this is going to be n. And we're going to look at I. We're going to look at I minus 1/2 and I minus 1, I plus 1/2, and I plus 1. So first we need to get all the midpoint values for this second version. We get all the midpoint values at I minus 1 for time step n plus 1/2. N minus 1/2, n plus 1. So all of the midpoint values we get. So from this 2 points we get this one. From these 2 points, we get this one, and so on, all along our mesh. And we're getting the midpoint values here. And then next, we do a corrector step that takes you to this is obviously the value that we want. ui at n plus 1, and we do it by taking the midpoint values and using these, as you can see in our formula, together with this one. This turns out to be very useful for nonlinear problems, but a little messy to use. So the next scheme that we're going to see, which has all the advantages of this, but it doesn't require you to keep all the half mesh points, is called the MacCormack scheme, and that was also extremely famous and used for many years, and we'll look at that. So this is a second order method, like Casey here just said. Second order. And in fact, for linear PDEs, it is the same, it's equivalent, completely equivalent, you don't get anything, to the single step, Lax-Wendroff. But the advantages come when you have nonlinear problems. And now we look at the MacCormack method. I was promising that we'll look at this alternative. So this one is also a two-step method, and step 1 uses a forward difference scheme, and we're going to call U star this temporary value for the solution, or the predicted value, and so we use a forward difference, and we write U star at I minus UN at I divided by delta T equals to minus C, and I plus 1 minus I minus UI, and both of these at time n divided by delta x. And step 2 uses a backward difference scheme with time step delta t half. So we have un plus 1 half, no, sorry, un plus 1 at I minus un plus 1 half, correct, 1 half here. And so this is divided by delta t half now, equals to minus C. And here we use the predicted values, the temporary values of the solution at I and at I minus 1. Now, also we need to replace the value un plus 1 half by the average, the trick that we've used in the Lax-Wendroff. The average of the values on each side. So that would mean that we want to use 1 half of u at n, and the previous value, which is our temporary value, our predicted value here. So we are left with, finally, the predictor step, which is u star I equal to uni minus C delta T over delta X UN I plus 1 minus UNI, and our corrector step is going to be UN plus 1 I equal to 1/2. Here we have our average, UN at I plus U star at I minus C delta T over delta X and U star at I minus U star at I minus 1. Again, this is a second order method. With stability requirement that the current number be less than 1. And for linear, similarly to the two-step MacCormack, two-step Lax-Wendroff, for linear PDEs, it is equivalent to the one-step Lax-Wendroff. Also, we can alternate. It is possible to reverse the order of the backward difference and forward difference in 2 consecutive steps. So we can alternate forward difference, backward difference, and then backward difference, forward difference. You can alternate that, and it turns out that this scheme works very well for nonlinear problems. And in general, the MacCormack method is very good for nonlinear problems. And you notice that it eliminates the requirement to calculate, like you noticed, all the values at the intermediate mesh points. So that's the advantage over the previous one. Okay? All of these methods are going to be particularly useful for nonlinear convection. This is going to be our next assignment. Nonlinear convection. So the only difference is that we don't have a constant velocity. We have a velocity that is actually the changing solution here. This is our inviscid Burgers equation. And this is very important in fluid mechanics because the majority of PDEs in fluid mechanics are nonlinear. So by studying now we can graduate now to the nonlinear convection equation after exhausting really everything that we can learn from the linear convection one. And we'll find that this is very important for fluid mechanics. And in fact, one can learn a lot of things from just studying this very simple hyperbolic equation that are especially important if you are studying Euler equations, which are used in compressible flows, widespread for compressible flows, just Euler equations. And also, in general, in fluid mechanics, the nonlinearity dominates over the viscous. In most problems, you will find that high Reynolds number means that, of course, the balance between the inertial terms and the viscous terms is such that the viscous terms are very small, and so the nonlinearity dominates, except for the few cases, very particular cases of highly viscous flows, Stokes flow approximations, where you can, those are a class of fluid problems. Very particular class of fluid problems where this doesn't apply, but in general, the nonlinearity will be dominant, and therefore our conclusions from studying the nonlinear inviscid Burgers equation have consequences, important consequences for computational fluid dynamics. So it's a classic problem. We'll study the 1D problem first. And this classic first-order hyperbolic equation can be written in the conservative form. The conservative form just means that all of the space derivatives appear under the gradient. And if you don't remember that, just go on Blackboard and look at that under our reading section. It's a very short reading that explains, you know, what this means. And we're going to use this now quite a lot, and we're going to use it from now on. Also, it's going to be useful for some other things that we're going to introduce later. So in conservative form, we can write it as du dt is equal to minus u. The u I'm going to put inside the derivative by writing d dx of u squared half. You can see these two things are equivalent. So to write it in a more general form for general nonlinear equations, we could write du dt equal to minus d dx of something that we call the flux, which let me just call it capital E, where of course E is equal to u squared half. And this allows us to write things in a more general form so that we can use them for other nonlinear equations. Now, the physical interpretation of the Burgers equation, we've discussed it before, because of course this was your step 2 of the previous assignment, is that this is a wave which propagates with different speeds at different points of the solution. And eventually, we get a shock. So we're going to develop the different schemes that we've already studied for convection equations: Lax-Wendroff, and MacCormack. And the idea is going to be the following assignment, and let me just skip to the assignment and leave you with this because we'll do the details next class. And the assignment is going to be, this is going to be our practical module for the nonlinear problems. You will do the following test. It's going to be an initial waveform that has just a discontinuous distribution, 1 and 0, the values 1 between 0 and 2, and 0 between 2 and 4. So basically it looks like that. And we're going to investigate the propagation of this discontinuous function under the inviscid Burgers equation with the Lax-Friedrichs method, number 2. So this is a 3-step assignment. Step number 1 is Lax-Friedrichs. Step number 2 is going to be Lax-Wendroff. And step number 3 is going to be the MacCormack method. We're going to start with something rather crude, say delta x and delta t. I'm going to give you, say, start with 0.1. Then change our ratio between delta t and delta x from 1 to, say, 0.5. And we're going to then see with this the effect of the Courant number. And then change to a finer mesh to see the effect of the step sizes. And of course, we wanted to make some conclusions about these schemes and which one is best for the nonlinear problems and so on. And I'll go over that next class, the different schemes for each for this nonlinear problem. And then you'll have a little something to do on spring break. Shouldn't be too much work though. This is going to be not hard, I hope.